to continue on, we're going to move into, for the book, this part about gas exchange, and then talk a little bit about transport of gases. Now, really, if we go back to that original set of functions, gas exchange is external respiration and internal respiration, and transport of gases is what takes place in between them. But gas exchange in either setting is closely related. So we're going to look at both of those together and then look at what happens in between. Now, to understand what's happening in gas exchange, we need to learn a little bit more about how gases work, some laws that have to do with it. And we've already talked about what's called Boyle's law, which was just the pressure-volume relationship that I talked about before. What I want to do next is to talk about a couple of other laws about gases. And I'm going to use stuff from this presentation to address them. So first off, this is the pressure-volume relationship just from another book. I have this picture. Then the next thing I want to talk about is what's called Dalton's law. Dalton's law defines this concept of partial pressure, which is the pressure of an individual gas within a mixture. So to explain it, there's this video here that I think it does a pretty good job. It's an odd little video. It's sort of, I don't know, got some presentation aspects to it that make it sound very, or seem very juvenile. But what it's discussing is a somewhat advanced aspects of the physical laws of gases. So it's a little strange, but it's a good explanation of things. Oh, I keep doing that.
What I have here is a balloon filled with ordinary air. Air is a mixture of gases, and you probably have thought that air was mostly oxygen. After all, oxygen is the piece that you're most interested in. You need it to survive. In fact, air is mostly nitrogen, N2. It's about 78% nitrogen and only 21% oxygen. What we're going to be talking about in this section are mixtures of gases. And the question that we're going to consider here is, we have a balloon. There's pressure from the gas on the inside of the balloon exerted against the outside of the balloon. If it's a mixture of nitrogen and oxygen, how are the forces of the individual gases related to pressure, and how are they related to the total pressure of the balloon? So in other words, each of the individual gases presumably exerts some pressure, and how is the component of each of the individual gases related to the total pressure of the balloon? And get rid of this. To answer that question, what we need to do is define a quantity first called the partial pressure. Okay. So here we have a mixture of gases. It's inside a container of volume V, and each of the individual gases is indicated by different dots. So we've got some red dots and we've got some blue dots. You know, what I want you to think about is, suppose we took everything out of the box except for the red dots. So we have a quantity of gas A in the volume V, and we can measure with this pressure gauge the pressure due to A just in the box all by itself. And we're going to call that quantity the partial pressure of A. So again, piece of A, the partial pressure of A, is equal to the pressure due to A as though it were alone inside the container. Okay. This is in the context, again, of a mixture of gases. Well, we can do the same for B. B, let's say, are the blue dots. We can have just B inside the box. We can define piece of B as the pressure due to B alone in the container. And now we get to Dalton's law. John Dalton, in the early 1800s, discovered that the total pressure exerted by a mixture of gases equals the sum of the pressure of the component gases. And this is now known as Dalton's law of partial pressure. If we look at an algebraic representation of Dalton's law, it says that the total pressure inside the container is equal to the partial pressure of A plus the partial pressure of B plus the partial pressure of C plus whatever else might happen to be in the container. And the really important point of this is that basically what this says is that A is oblivious to the presence of B and C. And similarly, B doesn't know that A and C are in there. So the gases don't even interact at all. And that is a tenet of the ideal gas idea, that the particles are so far apart that they're not really even interacting with each other. And so it really doesn't much matter whether the gas.
Okay, so that's part of a larger lesson, but what he covered there addresses what I'd like to talk about. So let me go back to the book for a second. Just really annoying video there. In this table and the figure below it, it kind of addresses what he was saying. Now, the figure below is very close to the picture that he had drawn of the volume and partial pressures of two different things. So here we have a mixture of two things, which they're saying are oxygen and nitrogen, different colored dots. And they have a particular pressure together. If we could remove all of the oxygen and leave the nitrogen, we'd see something like this, and that would have a different pressure. Or if we could remove all the nitrogen and leave the oxygen, we'd see this and have that particular pressure. That's the idea behind partial pressures. The partial pressure of oxygen is the pressure of it by itself that contributes to the overall. So you can't see the numbers here in the figure very well, but the partial pressure of oxygen plus the partial pressure of nitrogen adds up to the total pressure of those two together in this figure. Okay. The numbers they're using are the ones out of the table up above. And this is the composition of the air that we breathe and the partial pressures of the different components. There's a little mathematical error here, which is kind of minor, but so the gases that make up the air we breathe are mostly nitrogen, oxygen, water vapor, and carbon dioxide. 78.6% of the air we breathe is nitrogen, 20.9% is oxygen, 0.04% is water vapor, 0.004% is carbon dioxide, and then the rest is others, carbon monoxide, and et cetera, various things. Very small trace amounts of other things in there. That adds up to 100%, okay, with some rounding. The partial pressures are listed here. The partial pressure for other is actually incorrect, but it doesn't really matter for what we need to do, because we can kind of ignore the others, and we're just concerned with these main four. We can't actually measure just the pressure of nitrogen. We couldn't seal off this room and suck everything out of it but the nitrogen and see what the pressure is. That's not realistic. It's much easier to just do it by taking the total pressure, which is 760 millimeters of mercury. That's air pressure at sea level, and multiply it by the percentage of each percentage composition of each gas. So 78.6% of 760 millimeters of mercury is 597.4 millimeters of mercury. 21% of 760 is 159, et cetera, et cetera. 0.0006% of 760 millimeters of mercury is 0.005 millimeters of mercury. They just made a little calculation error there, but that should be obvious. There's less of the other things than carbon dioxide, so the partial pressure has to be less than carbon dioxide too, and the number's obviously not. So there's an error there, but again, it's not terribly important. We don't care about those. Yeah.
I'm trying to remember if Dalton incorporated into his law, but the partial pressure of an individual gas is equal to its mole fraction times total pressure of a, container.
Okay.
Container.
What's the question?
Oh, I don't know why the concept of mole fraction times the total pressure.
Mole fraction is percent composition. It's just, if we were to say there's X number of moles of gas molecules in that container, the fraction of that is whatever. That can be expressed as a percentage. So, and expressing it as a percentage gets out of trying to figure out the number of moles. Okay, it just sort of standardizes the numbers there. So really, to get these numbers, it's just a matter of multiplying the total by the percent composition of each thing there. Okay. So that's how the book presents what that video just showed. The other thing in the presentation that I want to show you here is explaining Henry's law with a picture out in another textbook, but I think it's a nice picture to understand what's going on here, with a few reservations. Now, the picture is showing a beaker, say, that's half full with a liquid, and then the other half of it would be full with a gas. That's based on the dotted line here, which would be the original volume. If the lid's pushed down from where the dotted line is to here, that's going to compress the air within that part of the beaker. Again, pressure-volume relationship. So the volume is decreasing, maybe by half, and so the pressure in here increases by twice, doubles. What Henry's law is basically saying is gases dissolve in liquid. That's about it. Okay. Now, it's a little bit more complex than that, but basically the idea is gases move through air phase and liquid phase equally, kind of. Okay, and I'll explain the soda can there on the side to explain a little bit better. But the idea is gases can dissolve into liquid, and how much it dissolves in there is just a matter of equilibrium. Whatever the pressure of gas is in the air phase, the gas will dissolve into the liquid phase at that proportion. When we talk about how much gas is dissolved into a liquid, we actually describe it by its partial pressure. Okay? We don't say that it has a concentration. If the partial pressure of carbon dioxide, say in this area here, were 50 millimeters of mercury, then when the carbon dioxide diffuses into the liquid phase to equilibrium, we would describe everything in here as being 50 millimeters of mercury partial pressure for carbon dioxide, regardless of whether we're talking about the air or the liquid. Okay. Actually, I oversimplified things a little bit, but that's plenty for what we want to understand. Now, the soda can on the side gives you sort of a real-world example of what this really means. So at a soda, Coca-Cola bottling company or something like that, where they're putting the flavored syrup of Coke into the can, and then also force carbon dioxide gas into that can at high pressure. Okay? We just saw that in the air around us, the partial pressure of carbon dioxide is 0.3 of a millimeter of mercury. So they force it in there at higher pressure. I don't know if it's 50 millimeters of mercury or not, whatever. They force in extra carbon dioxide. Now, it's probably replacing something else. So it's not a high pressure gas injected into that can necessarily. I am not a Coca-Cola bottler. I don't know the exact procedure. But anyways, there's a lot of carbon dioxide put in there. And so when the can is sealed, the carbon dioxide dissolves into the soda at that proportion. So it has whatever partial pressure inside. And then at the bottom, the lid is removed from the beaker. And so the air pressure the air phase, equilibrates with the rest of the air. And then the gas that's dissolved into the liquid will equilibrate with the air. So if we look at the soda can, when you open a soda can, the air phase at the top of the soda can will very quickly equilibrate with the surrounding atmosphere. So here's a closed soda can, and there's a pretty high partial pressure of carbon dioxide in the air up there. We pop that open, and carbon dioxide rushes out very quickly so that the air phase equilibrates with the air outside the can. Then the carbon dioxide that's dissolved into the soda will diffuse out until it reaches equilibrium. And when it reaches equilibrium, that's when the soda is flat. It doesn't have any more carbon dioxide in it than the air around it. Now, you certainly know from experience with soda, if you've had soda before, that it doesn't instantaneously turn flat. It takes a little bit of time for the gas to actually diffuse out. In a little video when he was talking about Dalton's law, he was talking about the ideal gas concept. What that is when we're talking about gases with these kinds of laws, we make an assumption that's fairly correct, which is gases operate independently. The distance between any two particles, an oxygen molecule and a carbon dioxide molecule, or a nitrogen molecule, or a water molecule, floating around the air around us, the distance between those are so great on the scale of molecules that they're highly unlikely to ever interact with each other. Now, it might happen, but the ideal gas concept is basically, we figure it doesn't happen because the actual occurrence of two molecules running into each other is so low, we'll just treat it as if it doesn't happen. That's not actually true of gases in a liquid environment, in a liquid phase, because the water molecules are going to be quite close to each other. So as carbon dioxide molecules are moving around within the soda, they're not going to just easily move right out the same way that the carbon dioxide in the air phase moves right out here. So it takes a little bit of time for things to get out because it's got to push through all of the water molecules. Okay. Again, a little bit of an oversimplification, but soda doesn't go instantly flat because it does take a little bit of time for the gas to diffuse out. Okay. So that's Henry's law. And the real take-home message of Henry's law for what we're dealing with here is really just gases dissolve into liquids. Okay? And when we talk about them, we'll still be using partial pressure, whether we're talking about the gas within an air mixture or within a liquid mixture, because they kind of act the same way in both situations. So those are the laws that are presented here in the book. Okay, so this is the Dalton's law stuff about partial pressures, and then Henry's law is about solubility of gases and liquids. And then after that, they go on to present us another table, which is about the partial pressure of gases in the air in our alveoli. And it's not exactly the same as the air around us that we're breathing in. When air comes in, the amount of oxygen, the percent composition of oxygen will change because a lot of that oxygen continues into the blood. It leaves the air and goes into the blood. So there's less oxygen there. And there's more carbon dioxide and water vapor in the air because, the water vapor because we've hydrated the air as we've breathed in, like I talked about for the nasal cavity earlier, and carbon dioxide because we're exhaling that. Okay? Because these are all changing relative to the atmospheric air, the amount of nitrogen percent composition goes down. The nitrogen isn't changing at all. Nitrogen as a gas, according to Henry's law, can dissolve in liquids too. So we have nitrogen gas in our blood, but we cannot do anything to nitrogen gas. N2 is two nitrogen atoms triple bound to each other. And we do not have the enzymatic fortitude to break a triple bond, okay? We have enzymes that can break the occasional double bond. There are lots of enzymes that can break single bonds, but we do not have any enzymes that can break triple bonds in anything. So when we inhale nitrogen, yes, it does get into our blood, but it doesn't do anything, and it just leaves our blood. So this change here doesn't really have anything to do with nitrogen moving in and out of our blood. It's really just a recognition of these numbers are changing here, so its percentage composition goes down. And likewise, the partial pressures will vary a little bit too. The partial pressures we're interested in is oxygen is a little bit above 100 compared to the 159 in regular air. And carbon dioxide is, this says 47, some sources will say 45, somewhere in that range, compared to the 0.3 millimeters of mercury partial pressure of carbon dioxide in the air around us. Okay. Carbon dioxide is much more concentrated in the air in our lungs than it is outside. When you exhale, a lot of carbon dioxide is coming out of your mouth based on these numbers here, but it diffuses into the atmosphere around us very quickly. It doesn't really make huge changes in the carbon dioxide levels around us. So this section here, talking about ventilation perfusion, is just getting at the fact that the gases, as they're moving into your lungs, are changing their percent composition a little bit, because some are perfusing into the gas, into the liquid phase of blood and that sort of thing. And then it gets into gas exchange. Now, gas exchange is both external respiration and internal respiration. I'm going to use this picture mostly to talk about both of them because it has the most information that I want to cover. There is a mistake in this picture, and first edition of any textbook is going to have some mistakes, and they just have to be caught. And this one is seemingly kind of minor, but it does make a big difference in what we're following here. Okay, so here we have an alveolus. So this is the air phase in our lungs. And here we have a red blood cell in the blood. So this is a liquid phase in our blood, obviously. Oxygen moves into the blood and carbon dioxide moves out of the blood. This is going to happen actually because the partial pressures for each are independent. Partial pressure of carbon dioxide in the blood is somewhere close to 40. And we just saw that in the alveolus, it's around 47, according to the book. So, nope, I said that wrong.
25.
No, it's higher in the blood, not 40, it's higher in the blood. Maybe it's around 50 or something. I don't remember. But anyways, it's higher. And we know that because the pressure is higher in the blood than in the alveolus, and carbon dioxide moves out. Okay. The pressure of oxygen is high in the alveolus, above 100, 104 about. And the pressure in the blood as it gets to the lungs is quite low. I think that's the 40 that I'm thinking of. So oxygen moves into the blood very rapidly down its pressure gradient. Carbon dioxide moves out of the blood into the air, down its pressure gradient too, but out of the lungs. They move independently. And again, this is back to that ideal gas concept. The gases don't really interact with each other, so we treat them mostly independently. Now, oxygen can go two places in the blood. It can dissolve directly into the plasma. That's actually a very, very minor component of what oxygen does. About 1.5% of the oxygen in our system is just dissolved directly into the plasma. The other 98.5% goes into the blood. So that just incredible disparity between the two will basically ignore the dissolved in the plasma stuff because there's nothing happening there. We're just going to pay attention to the oxygen that goes into the red blood cell. Now, oxygen combines with hemoglobin. Hemoglobin is abbreviated HB. The other H in this, HHB, is talking about hemoglobin that's bound to a hydrogen ion. I would more often call that protonated hemoglobin, because a proton is a hydrogen ion, but we would abbreviate it that capital HB. Okay. When oxygen and the protonated hemoglobin come together, this arrow should be pointing the other direction. The oxygen binds to the hemoglobin, and the hydrogen ion is released. Okay, so that's what oxygen does. It comes in and it displaces whatever is attached to the hemoglobin. It also displaces carbon dioxide that's attached to hemoglobin, which is not exactly shown here, but it is true. We'll get to the carbon dioxide in a little bit. So when carbon dioxide is released from hemoglobin, there's hemoglobin ready to pick up more oxygen. And that does happen, although it doesn't quite stress that here. Most of the hemoglobin is protonated. And so when we have oxyhemoglobin, we have a lot of hydrogen ions. Now, the hydrogen ions are going to go and associate with this molecule here, which is called the bicarbonate ion. When hydrogen ions, which have a positive charge, and bicarbonate ions, which have a negative charge, come together, they make this molecule here, H2CO3, which is carbonic acid. Now, carbonic acid is the combination of CO2 and H2O. Okay, H2CO3, we've got two H's, three O's, and a C, which would be a water molecule and a carbon dioxide molecule. That's what carbonic acid is. We break down carbonic acid using the enzyme called carbonic anhydrase. The name carbonic anhydrase describes that reaction. Okay, carbonic acid is anhydrated, which is just a weird chemical way of saying dehydrated, or we remove water from carbonic acid. And when we take water out of carbonic acid, what's left over is the carbon dioxide. So this enzyme breaks down carbonic acid into carbon dioxide and water. The carbon dioxide then is released into the alveolus to be exhaled. Okay. There's also carbon dioxide coming from hemoglobin, like I mentioned a second ago, and there's carbon dioxide dissolved directly into the plasma, which comes out. Now, I said that the oxygen dissolved directly in the plasma is very minor. The carbon dioxide dissolved in the plasma is a little bit more of the amount of carbon dioxide that we're talking about there, but it's still not a whole lot, and nothing's really going on with it. Most of the carbon dioxide is tied up in this carbonic anhydrase reaction, or the carbonic acid. And really, we could say that it's tied up in the bicarbonate ion, because carbonic acid will dissociate into hydrogen ions and bicarbonate ions naturally. Okay. And the CO2 that's in carbonic acid is still in the bicarbonate. So really, we could describe it as being in either way. That's where most of the carbon dioxide is tied up. Some of it gets held up with, bound up with the hemoglobin, and then a little bit of it dissolves directly in the plasma. Okay, so there's three arrows here for carbon dioxide because there's three actual ways. There's only two arrows for oxygen because there's only two ways that it can do its job there. Now, this picture is showing what's happening between the blood and the alveolus. There is this one mistake, the arrow between the oxygen reacting with hemoglobin and the oxyhemoglobin having given off hydrogen. That arrow should be pointing the other direction. Just a little mistake in how it's drawn. But this is external respiration. This is what's happening in the lungs, blood to the air. Internal respiration is basically the opposite. Now, this picture in the book is not exactly the same as this picture here, obviously. There's nothing drawn inside of the red blood cell. But on the left side of the picture, we have cells representing the tissue, just like on the left side of this picture, we have the alveolus, okay? And on the right side of the picture, we have the blood with the red blood cell. And the arrows are showing movement between the two. The arrows for oxygen going into the tissue in internal respiration point the opposite direction of oxygen moving into the blood in external respiration. So those arrows just go the opposite direction. Same thing with the carbon dioxide. Carbon dioxide leaves the tissue and goes into the blood for internal respiration, and it leaves the blood and goes into the air for external respiration. Okay. So the arrow directions here are just opposite for internal respiration. Likewise, what's going on in the red blood cell is just running the opposite direction too. Okay. So carbon dioxide comes into the red blood cell from tissue. It combines with water. Carbonic anhydrase puts those together to make carbonic acid. The enzyme is called carbonic anhydrase. It's describing breaking down carbonic acid. But enzymes always work based on limiting factors in reactions. If you have more carbonic acid than water and carbon dioxide, then carbonic anhydrase will break down carbonic acid. If you have more carbon dioxide and water than you have carbonic acid, then the reaction will run in the other direction. Okay, and so we just reverse this arrow for internal respiration, and carbonic acid is formed by carbonic anhydrase. And then also we turn this arrow around because carbonic acid will break down into hydrogen ions and bicarbonate ions. The hydrogen ions will go back and take up the position that oxygen left, and we'll get the protonated hemoglobin, and the oxygen is released from the blood to go into the tissue here. Okay, so if we just imagine this picture is running in the exact opposite direction, and the left side of the picture had tissue instead of the alveolus, that would be internal respiration, which this picture is showing. They just don't have everything written inside of the red blood cell, but that's what's going on. Okay. So really the gas exchange part is just the exact same thing running in one direction or the other, depending on whether we're looking at oxygen coming from air into blood and carbon dioxide leaving blood into air, or carbon dioxide leaving tissue going into blood and oxygen leaving the blood and going into the tissues. It just, the things run backwards. And if we look at the partial pressures of the gases in the air, which we saw a table of earlier, versus the gas versus the tissues, the partial pressures will always fall in line with the movement of gases. The partial pressure of carbon dioxide is highest in the tissue and lower in the blood, so that carbon dioxide moves into the blood. And then once it's saturated carbon dioxide, the partial pressure there is higher than the carbon dioxide partial pressure in the air. So carbon dioxide leaves the blood into the alveolus. And oxygen is just the opposite. The partial pressure of oxygen in the alveolus is the highest point, and it moves into the blood until it saturates the blood. And then when the blood gets to the tissue, partial pressure of blood in the partial pressure of oxygen in the blood is higher than the partial pressure of oxygen in the tissue, so the oxygen moves into the tissue. Okay. It's just all driven by partial pressure there. So that's the end of the gas exchange portion, which is really external respiration and internal respiration. Transport of gases is what happens in between those two. The gases are moved from the lungs to the tissue, or from the tissue back to the lungs. Okay. For oxygen transport from the lungs to the tissue, here we have just the reaction of hemoglobin and oxygen when it comes together makes oxyhemoglobin, okay, which is kind of suggested there. This is a representation of the hemoglobin molecule. Each subunit, there are 4 subunits, has a heme molecule in it, and in the middle of that heme molecule is iron, and that's what the oxygen actually reacts with. Okay. The interaction of oxygen and hemoglobin is described in a graph like this, whoops, there we go, which is called an oxygen saturation curve. On the x-axis, we have the partial pressure of oxygen. Okay, 100 is actually a little bit lower than what it is in the alveolar air, but it's basically what it is in the blood. 40 is what it is kind of in the tissues. Okay, so there's some variation in partial pressure depending on where we are in the system, but it ranges between 40 and 100 millimeters of mercury. On the y-axis, we have the percent saturation of hemoglobin, percent saturation of oxygen in the hemoglobin molecules. Okay. If we look at the point where that curve hits 40 millimeters mercury, which is the lowest partial pressure of oxygen in the system, or where it hits 100, we're really talking about oxygen saturations between about 75 and 100%. Okay. The way that we measure oxygen saturation in the blood is using a device called a pulse oximeter. If you've been in a hospital, usually a little white plastic clamp over the end of the finger, it shines a light into the skin of the finger. And that light will be reflected by the blood in different colors depending on how saturated the hemoglobin is. Okay, when hemoglobin is completely saturated with oxygen, it's going to be very red, and so it's going to reflect light in a very specific wavelength. When the oxygen saturation drops, the hemoglobin overall will be less red, and so it'll reflect back in different colors. So the oximeter is really just looking at the color change based on saturation of the hemoglobin. Normal blood saturation, oxygen saturation levels using a pulse oximeter, which is looking at the overall amount of blood, not just the arteries or the veins, and it's way out in the periphery. It's not near the lungs. It's really going to be somewhere up here in the 95% range kind of thing. If somebody's exerting themselves, the number will start to drop down. Somebody's doing a stress test in the cardiac function lab, put them on a treadmill or a stationary bike and have them start exercising. The pulse oximeter will show that blood saturations would be dropping because the oxygen is being taken up by the skeletal muscle because of the exertion. Okay. But generally, you should see just changes in saturation in this region here. If partial pressure of oxygen drops below 40, then you'd see it down here, but that'd be very unusual. It shouldn't be less than 40 if homeostatic mechanisms are working properly. The curve also kind of shifts right around in here. It's pretty steep on this side. So below 40, we have rather rapid drop in oxygenation saturation. Above 40, this curve isn't quite as steep, and it starts to level out when it gets way up here. Okay, so most of the change in saturation is limited up into these upper percentiles, because that's more where the actual partial pressure is going to stay. Okay. Now, back to the book. I just showed you this picture. These two pictures here are showing some things that interact with the oxygen saturation. The middle line here would essentially be the curve we just looked at. It's not quite drawn perfectly the same, but the idea is your blood pH should be around 7.4, maybe 7.35. So that's your normal physiological pH. So that should be what oxygen saturation looks like normally, what we would expect here. This picture actually is drawn slightly differently, so it doesn't quite match up, but still the same idea. When blood pH changes, saturation will change with it. So in acidosis, when the blood pH is low, meaning that it's more acidic, saturation is depressed. So you can't carry quite as much oxygen in your hemoglobin. When the blood is basic or alkalotic, pH is higher, saturation is a little bit better. Okay. Now, really what corresponds to pH the most is carbon dioxide levels. And that's really because, well, where is that? Shoot. Of the carbonic anhydrase reaction. Okay. Carbonic anhydrase is really related directly to carbon dioxide levels. The more carbon dioxide you have, the more hydrogen ions you're going to have in your blood, and therefore the more acidic your blood will be. hydrogen ions in your blood can be cleared away by binding to the bicarbonate ion, HCO3 minus, to make the carbonic acid molecule. And then how fast you can break that down and release the carbon dioxide to exhale will mean that you can keep the blood pH lower and lower. Okay. If you have too much CO2, these reactions are going to run the opposite direction of what's in this picture, and you're going to have more hydrogen ions, and therefore blood pH is going to be lower, more acidic. Okay. So those are really tied together there. Yeah.
I mean, because the other diagram, just real quick, that you just all right, so I mean, this reaction could shift either way depending on the partial pressure of the given gas you're talking about, right? So,
Well, no. What I'm talking about is carbon dioxide, so it's only going to be affected by the partial pressure of carbon dioxide.
right, so for partial pressure, the individual gas could shift the reaction the other way. Should it be written as an equilibrium reaction?
If we were just talking about that reaction by itself, but we're talking about this reaction in external respiration, okay? So in external respiration, because the partial pressure of carbon dioxide outside is lower, there's going to be a directed movement of carbon dioxide out, okay? I'm just using this picture because that's where we have everything written out. So if we're just talking about this, yes, then we would have these arrows pointing both directions for equilibrium, and it would shift one way or the other based on the partial pressure of carbon dioxide. Okay. So back here, when the partial pressure of carbon dioxide is high, blood pH will be low, which is going to depress the saturation curve a little bit. Homeostatic mechanisms for the respiratory system are really trying to keep the blood pH up so that the saturation curve is going to be closest to its natural or regular condition there. Now, this other figure, I'm not going to spend a whole lot of time on, but it's in the book. I want to point out another thing that affects saturation is temperature. Okay, as temperature goes down, saturation's better. As temperature goes up, saturation falls off. The one reason why this is something to mention is as you're exercising and exerting yourself, your mitochondria, especially in your muscles, are going to start putting out a lot of extra heat as they're making lots of ATP. So your body temperature can go up. Maybe not to 43 degrees Fahrenheit, but it'll go up, and that's going to compromise oxygen saturation. Okay. So as you overheat when you're exercising, besides the fact that you're using up lots of oxygen anyways, you're also depressing your oxygen saturation, which can make make it a little harder to get oxygen to your muscles there, and they'll fatigue quicker. Okay. So, but this is the more important thing because it really gets at the regulation thing. When you're regulating breathing, really what you're doing is you're regulating carbon dioxide. The where was that? Actually, the process of breathing section of the book here, towards the end, has a picture, and I didn't go all the way down here after all of this, has a picture of the nervous system connections to the muscles for respiration. So the book describes these different structures a little bit more in depth. I'm not going to go into it too much, but in the medulla, there are a couple of nuclei that control the muscles of respiration. The dorsal group specifically is controlling the diaphragm and external intercostals directly. It's always sending out signals. It's autorhythmic, just like the heart, so that you're always breathing. The ventral respiratory group will affect the other muscles when needed, and they have to get input from somewhere else to tell them to do that. In the pons, there are some descending inputs that regulate how we breathe in different ways. One of them is an inhibitory and one of them is an excitatory input. What's not really pointed out here, but it is said up here, higher levels like the cortical areas of the brain and the hypothalamus can send information down to regulate this. And then also peripheral structures like in the aorta and the carotid arteries can send information in here to change things. The carotid body and the aortic body are monitoring blood partial pressure of CO2 primarily, which means also pH. The partial pressure of oxygen isn't really that central to what they're doing, although how they regulate partial pressure of carbon dioxide is going to have an effect on oxygen. What they do when your blood is a little acidic, it causes you to breathe more forcefully and deeper, faster and deeper. So you exhale more carbon dioxide and clear that out of your system. When you exhale, you're obviously going to inhale and then right after that. So you're going to draw more oxygen in, which is actually secondary to what's being regulated mostly here. When your partial pressure of oxygen in your system goes down, really the way that we respond to that directly is the kidneys tell your red bone marrow to make more red blood cells, which is not a great way to regulate respiratory function. But if there's a systemic change in oxygen partial pressure, then the kidneys will do something to deal with that. But really we're regulating breathing mostly about carbon dioxide. When you breathe carbon dioxide out, you're obviously going to breathe oxygen in right after that. So that'll sort of play into that. So the partial pressure of oxygen here is really secondary to the partial pressure of carbon dioxide, but pH and carbon dioxide really go hand in hand. So there'll be inputs coming in from the periphery that tell these structures to do different things, so you breathe differently. Yeah, okay. Now, there's a little section here after transport of gases with no figures and just describing a few things that have to do with how respiratory function can change. The one thing to point out here is about the relationship of altitude and air pressure. At sea level, which would basically be New York City, the atmospheric pressure is 760 millimeters mercury, as I've been saying, which would correspond to a partial pressure of oxygen of 159, which we saw earlier. As you increase your altitude, you're going to see these numbers change. At about a mile high around Boulder, the atmospheric pressures dropped quite a bit, and partial pressure of oxygen has dropped with it. Aspen, even higher, numbers go down, and then climbing up Pikes Peak or Denali or Mount Everest, the numbers get even lower. The partial pressure at the top of the oxygen saturation curve was 100 millimeters of mercury. When you get partial pressures of oxygen that are below that, you're going to have trouble getting oxygen into your blood. So hikers especially need to increase their oxygen supply, usually with oxygen tanks, to overcome that. Now, we're not actually at sea level, but we're pretty close. We can kind of think along those lines. I've always just worked with we're at sea level, but now we have the technology to figure out differently. I asked about this in my Tuesday, Thursday lecture class, which was the first class I was talking about this with. And if you're interested in doing this, you can also. Nowadays, some phones have barometric sensors in them. So you can download an app that'll measure the barometric pressure of the air around your phone and get a very accurate altitude number. So I had one of my students do that on this floor, and comparing that to the pressure of sea level, it said that we were 67 meters high. So that's, oh shoot, I did the math before. Oh, that's right, it's 232 feet, okay? That's how far above sea level we are on the 5th floor of this building, okay? The student who did that for me said that she would send me a screen capture of her phone using that app when she was on the 1st floor of this building. She never sent it to me. I'll remind her of that later on. But, so I was just curious exactly how high up we are from the 1st floor of this building. If you're interested and you have an iPhone 6 or a Samsung Galaxy, those have barometric sensors in them. You can download an app to run it. Other Android phones, I don't know if they have them or not. It depends. I thought mine did. It always said that it did, but it doesn't give me any barometric data. iPhones 5 and lower do not have it. But if you have an iPhone 6, there's an app for that. If you have a Samsung, there's an app for that. Yeah. When she did it, it said that we were 67 meters high.
We were 290 feet.
Okay. Sorry?
290 feet right now.
It could be something about barometric pressure changing with the weather in general. So I don't know how accurate that was. That was just the number we saw on the phone. Okay, so apparently I'm done. Have a nice day.
Yeah.
Oh my gosh.